Swayam Prabha. Digital India. Educated India.
So now we are going to discuss probability distributions. First, we need to know how data can be visualized. Now here, let us say there is a table and we have 50 data, and this data is regarding the height of, suppose, height of students in a class. There are 50 data points. Now if I want to visualize the data, what is the approach that we should take? Why do you want to visualize? Because we want to find out whether there is a pattern in the data or not. And if we want to visualize the pattern, then this can be done if we can have a frequency distribution of the data that we have. And we can plot that. First of all, we have to go for a frequency distribution, and then that data can be plotted in the form of a histogram. So if we want to go for a frequency distribution of the data that you see in the table, this is the frequency distribution table of the same data. What we have done, we have made groups. So we have made how many groups? 1, 2, 3, 4, 5, 6. The entire data set has been grouped into 6 groups, and each group has a lower value and an upper value. Like the very first group is 161 is the lower value, and 162.9 is the upper value. The groups have been chosen in such a way that the class width is fixed, which is 1.9. So 161, 162.9, 163, 164.9. If you take the difference between the upper value and the lower value, the difference is 1.9. We have fixed the class width, and this particular column gives you the midpoints of the class. So 161, 162.9, the mid value will be 161.95. So this way we have found out what are the midpoints for each class intervals, and they are here in the 1, 2, 3, 4th column. And now what we need to do is to find out how many data are lying within the class interval 1, class interval 2. If I say this is my class interval 1, this is 2, this is 3, this is 4, this is 5, and this is 6. In each class interval, we have to find out how many data are there. So that number is basically frequency. So these are the corresponding frequencies. So we get the lower value, lower and upper limits of the classes. Class widths are fixed, and within each classes, what are the frequencies that is available now. So this is the frequency values of different class intervals. Now we can plot it in the form of a histogram. So this is the histogram plot which you see at the bottom. And you see in each histogram, the frequency values are also written. So this histogram can be easily you can easily draw it by using an Excel. So what has to be quite familiar with the Excel, and if you have a set of data points, you can do all this job within maybe 10-15 minutes. So histogram, the moment we see it, we see there is some pattern, the way the heights of the histograms are available here. The class width of the histogram is governed by two important factors. One is the number of data which is available and the accuracy that we need. Based on these two, we decide what should be the class interval. Now, if the sample size is large, sample sometimes could be 10, 20, 30, 50, 100. In the example, we have taken a sample size of 50. Suppose we have 100, 200, 300 sample sizes. Then frequency distribution with smaller and smaller class intervals can be drawn. So if you have a large set of data, then the class intervals can be reduced, or the width can be reduced. And in each width, you are likely to get some data. And that will improve the accuracy. So when you have large volume of data, then it is possible to have more number of classes and with narrow width or narrow intervals between them. So like it is shown, there is a histogram here, and if we increase the number of classes, then the corresponding histogram will look like this. Class width have decreased. It has almost become half now. Now, if we continue this process, if we keep on reducing the size, the width we keep on reducing, the accuracy of the measurement will increase and the outline of the histogram will be indistinguishable from a smooth curve which is shown at the bottom. That you will only get very thin lines like this. Histograms are so thin. So that is how the outline would look like. So it becomes almost like a smooth curve. So this is how, first of all, the data points, if we want to visualize the pattern, we have to find out first a frequency distribution, then you plot them in the form of a histogram, and if you keep on reducing the width, as it is shown here, as you go from A to B, B to C, we get almost like a net, and if we draw this outline, gradually it will look like a smooth curve. In this, the areas of the rectangles forming the histogram represents the relative frequency. This is something very important to remember. It is the area that represents actually the relative frequency. Like in this case, the hashed area represents frequencies or proportion of values lying between A to B, like here, or this histogram. Here it is A to B is this. For a smooth curve, A to B is shown here. So if we want to know the relative frequency, then we need to find out the area of all these three rectangles in this particular case, or these 1, 2, 3, 4, 5 rectangles for the histogram B. And for the smooth curve, we have to find out the area. So remember, it is the area that's what is basically is the probabilities. These proportions are called the probabilities. So proportion of values lying between A to B is the probability that X is going to take values between A to B. So probability is basically the area of the rectangles in the case of histogram, and when it comes to smooth curve, we need to know the area of the curve between A to B, and for that we need to know what is the equation of this curve. If we know that a function that represents the equation of this line, outline, which is representing the probability density curve, then we can easily integrate between the two limits A and B to find out the area between A to B, and that will be the probability that the x value is going to take between A to B. This is how we can visualize the development of probability curve. So the probability, one probability curve now is shown, which is a smooth curve, and let us say the right hand side maximum value is x max and the left hand side minimum value is x mean, and the height of the probability density curve at any value of x is given by y as a function of x. That means basically this is what is describing the equation of this line. At any point x is along the x-axis, this random variable is shown along the x-axis. So what is the value of y? This is my y. So if this is known, we can find out what is the height at a given value of x. So to know that, this is the relationship we need to know. That is basically simplistic, simple way we can say we need to know what is the equation of this line, equation of this curve. The probability of x lying between the two limits A and B will be whatever is this. Suppose the equation of x, equation for which describe this line, is represented by fx. So it will be simply that we need to integrate fx dx over the limit A to B, and that will give me the area between A to B, like it is shown here. From A to B is this. So this is basically representing the area shown by this, the blue part of the blue part under the curve. So that is will be the probability that x is going to lie between A to B. So probability is basically always the area. So total area under the curve, the total probability has to be always 1. That means in this particular case, x integration of fx, x mean that dx should be written here. This total area is supposed to be 1. If the limits, lower limit is minus infinity and upper limit is plus infinity, then the entire area from minus infinity to plus infinity is be always 1. So for any probability curve, the total area has to be always 1. So whether a particular density function, this fx, we call it probability density function. Whether this is the right probability density function or not, there is a check, and that check is that if we integrate this function from minus infinity to plus infinity, or if the limits are given in a particular case, and if we integrate, if the value comes 1, then only we'll say this is the right density function. So fx is representing the density function. That is the density at a given value of x. And density means the value of y at a given value of x. Now there are different distribution curves. Some curves are shown here. They take varieties of shape. Some are symmetrical in nature. This is called uniform distribution. This is known as exponential distribution. This is known as positively skewed distribution. There are many more distributions. All the distribution we cannot learn in one course. It's not possible. So we'll take up those distributions which are relatively easy to learn and more useful in the beginning. So if you look at the probability distribution now, so there are two types of distribution. One is called discrete distribution and the other one is continuous distributions. Some standard probability distributions. Standard distribution can act as a model for the real data. So we're going to learn some standard ones only. It can act as a model for the real data, and each distribution has certain parameters which will define or describe the distribution. Individual distributions of same type are distinguished by different values of the parameters. So like here as an example, you learn more about them gradually. If the distribution is normal, the parameters are mean, mu and standard deviation, sigma. These two are the defining parameters of normal distributions. So that could be a large number of normal distributions. They will differ each other when their mu value changes or their sigma value changes. So there is a large number of normal distribution could be there, because there is no limit to the value of mu and no limit to the value of sigma. But only two parameters will describe the normal distribution. Exponential distribution, the parameter is alpha, which is 1 upon mean. That is what the parameter of exponential distribution, and it has only one parameter. One parameter will be able to describe the exponential distributions. We don't need the other parameters. So why is it so? We will gradually learn them. Another distribution is binomial distributions, and there are two parameters here also. One is number of trials or number of experiments, which is small n, and another one is probability of success in the trials, which is p. So these are the two parameters for binomial distributions. By taking different values of n and p, we can generate various types of binomial distributions. So you can practice that using the Excel, and you can have to go to the binomial function which is there in the, if you go to the statistics part of the Excel, and you can choose different values of n and p, and you can see that how the distribution pattern is actually changing as you change the value of n or value of p. Poisson distribution also has only one parameter. This parameter is generally represented by the value lambda. So these are the symbols. These symbols can vary from textbook to textbook. Some textbooks it is lambda, some textbooks it may be some other Greek letter they might use it. Now we'll go to mean and variance of discrete probability distributions. Here is a discrete distributions where the values of the discrete variable x is x1, x2, x3, xi up to xk. So discrete values of x, when you say this is discrete, that basically means the values that it can take will be either 0, 1, 2, 3, 4, 5, 6 up to k. It cannot take a value 1.2 or 2.5. Such values it cannot take because it is a discrete in nature. It will only take integer values. So this x1, x2, x3 that we have written here, these values could be any one of those. So, and these are the frequency column. This is the relative frequency column. It is f1 divided by sigma fi, which is n. So this column is relative frequency, and relative frequency is basically is the probability. So relative frequency and probability are basically same in the case of discrete distributions. So distribution of x is defined by a formula for calculating the probability that x is going to be xi is going to lie between 0 to k. This is maximum value, this is the k. So mean is calculated from the frequency table. How to calculate mean, I think you have already learned. That is, if I want to know the x bar, I have to do this sum of fi xi divided by actually sigma fi. So sigma fi is equal to n. So I have written it here, that's why n. And fi xi, that means each frequency has to be multiplied by the corresponding value of the discrete variable x. So if we multiply them and take the sum, that is what will, and then divide by n, that will give you the mean. This I have written this way. So sigma xi fi by n, or fi by n becomes my relative frequency, which is given in the column 3. Okay, now relative frequency is the estimate of probability. It is a very important statement, so that's why it is underlined. Now, as the sample size small n increases, the relative frequency becomes exact probability and can be replaced by pxi, which we have done in the last column. And the sample mean becomes equal to population mean because the n is increasing. These values are set. If I increase n, that means the values of f1, f2, f3, these numbers are going to increase. Suppose sum of fi is 50, it could be 500 if we can make it, or 300 or 200. So if n increases, then the relative frequency becomes more and more accurate with respect to the probability that the variable x is going to take a value x1, or probability of value of variable x, capital X, is going to take a value x3. X3 may be suppose 2. That is going to be px3, we write it. So as n increases, sample size increases, is become close to the population. In that case, the sample mean, the way we calculate, becomes the population mean, mu. And therefore, the population mean, mu, we could write, we use the same equation, whatever we have written it here, same thing, we bring it here now. But we replace the relative frequency fi by n by pxi, because we write these to be the probabilities. Therefore, the mean is sigma xi 0 to k xi into pxi. So each value of this variable multiplied by the corresponding probabilities. If I make one more column here, multiply these two, and then add them. That will give me the population mean. So that becomes the formula of population mean. It is simply population means sigma xi pxi, I varying from 1 to k. K are the number of discrete values that the variable x is going to take. Now let us say we want to find out the mean, and here is an example. Loom stoppage data is shown in the table. Calculate the mean stoppage rate. So here is a table where loom stoppage data per shift is given. That is, no stoppage, frequency is 35 times in a shift. It is very unusual, but let us say this is the data we have chosen. Then only one stoppage, the frequency is 25, the two stoppage 20. This is the corresponding data. It is loom stoppage, number of times the loom stopped in a shift, and the corresponding frequencies are given here. It could be, for that matter, any machine. You can imagine in any industrial process, any machines. There is a bunch of machines working in a shade, so we are interested to know that how many machines are had to stop or stop, because whatever may be the reason in a shift of 8 hours, and the data we collect and we represent it in terms of frequencies and number of time the loom stopped. So if then I find out the corresponding relative frequency, because total of this frequency is 100. If I add these values, 35 plus 25 plus 20 plus 10 plus 5 plus 5, it will give you value 100. So 35 by 100 is 0.35. 25 by 100, 0.25. Like that, if these are the relative frequencies. And relative frequencies becomes my actual probability. So the last column, we write it probabilities. So now you have to calculate. So you know the formula. Mu is this. So what we do? We'll write sigma xi pxi. So xi values are 0, 1, 2, 3, 4, 5. So 0 into 3.35, 0.35 is here. This is 0. So we multiply these two. Then 1 into 0.25. So we take this value, and here is 0.25. So we go like this and multiply them. So this way continue for all the rows. These are the corresponding values you will get, and when you add them together, you get a figure 1.4. So the mean stoppage rate per shift is 1.4. Now comes the variance calculation. Now we take the same table, we add one more column here. This is the new column that we have added. See, variance, as we have learned from the basics, that it depends upon the deviations. Variance is a measure of variability. Variability with respect to the central point, that is the average or the mean. So how much variation is there with respect to mean? We need to know what are the different deviations from the mean. So we have to calculate the deviations. So, and the deviations are shown here, x1 minus mu, x2 minus mu. These are the corresponding deviations. But we all know the deviations could be positive or negative, and therefore, and if we want to find the total deviation, it may work out to be finally 0. because some deviation will be always positive, some deviation will be negative, and sum total is going to be 0. So just by finding out the total deviations, will not be able to really measure the variability, because that will give you the value which is 0. So what we need to do is that we take sum of square of all deviations, which is xi minus mu whole square, and if we want to know the sum of square, we have to multiply them by the respective frequencies. This deviation has f1 frequency, this deviation has f2 frequency. So corresponding frequencies we have to multiply. That's why fi is coming here. If the frequencies are not there, then we need not to. We simply multiply x1, we simply then do xi minus mu whole square and add them together. If it is not a frequency distribution table, but frequency distribution table means frequencies exist for each and every value of the variable, and hence whatever is the deviations, this deviation exists f1 times, this deviation exists f2 times, similarly this deviation exists fk times. So you have to find out the total deviations in this case, and that basically means you have to multiply each individual deviations by the corresponding frequency, deviation square, sorry, not deviation, deviation square, and then multiplied by the corresponding frequency, and then sum them up. So you have to, that is what has to be done. And after doing this, we have to find out what is the average. So we have to, the total is n, total frequency is n. So this sum of square of deviations, then we find out the average of that. So in the numerator it is coming sigma fi xi minus mu whole square, which is sum up from I equal to 1 to k, and then to get the average we divide by the total number of frequency, which is small n, or small n is shown here. And if I do this, I can write the same thing in this manner. But is I replace fi by n as pxi. So the probability distribution of a discrete random variable x is a list of possible values of capital X together with their probabilities. You should also satisfy the condition that each fx should be greater than 0 and sigma fx has to be equal to 1. So this is how we can calculate the variance, that is deviation square multiplied by corresponding probabilities and then sum them up, we get the variance sigma square. Now for the same example, if we want to find out what is the variance, then we will go like this. So we find out the probabilities, we make the third column. So probabilities are nothing but relative frequency. Then we find out we know we have calculated the mean earlier, so we find out what are the different deviations and square values are here. So mean was calculated 1.4. So now 3 minus 1.4, 4 minus 1.4, then square them. That is the deviation square, and this is the value. Then all those deviation square multiplied by corresponding probabilities, pxi. These values are here. So 1.96 multiplied by 0.35. Here 0.16 multiplied by 0.25, that you get here. Again 0.36 multiplied by 0.2, it is here, and this is the value. This is what you keep doing, and then you find out the sum total here. This is 2.04. So sigma squared is basically sum total of all these values, which is 2.04. So this is the variance, and if we are interested in standard deviation, we take the under root 2.04, and that gives me a value which is the standard deviations. This is how we calculate the variance. So whatever we discussed, that is about the discrete distribution. Now mean and variance of continuous probability distributions. The logic is exactly same. The approach is also same. So once you understand the discrete probability distributions, how to calculate mean, how to calculate variance, exactly same approach will be applicable to continuous distributions. Only that sign sigma is going to change by the sign integration. So here is a smooth curve shown, which is because it's continuous distribution, it will look like a smooth curve. So curve is shown. This is a probability distribution curve where this is x and this is basically your y, which is a function of x. So area under the probability distribution curve represents the probabilities. So probability of the variable x falling between xi and xi dxi is shown by the hashed area. That is the area shown by these blue inclined lines. So this line, these lines from here to there, this area is basically the probability that x is going to take values between xi to x. Suppose this is xi plus dx. If the width of the interval is small, the hashed area will be almost like a rectangle. Like this. Suppose this width I make it very, very small. It will be almost like a rectangle because this height is going to be so low. If I further reduce it, a dx, I reduce it further smaller and smaller, it will be almost like a rectangle. So how to find out the area of a rectangle? It is width multiplied by height. So probability of x lying between xi and xi plus dx basically means the area of this rectangle, height into width. So height is fxi and width is dx. If we multiply these two, this will give me the area. So that becomes the area. So the contribution to the mean by the values in the interval xi and xi plus dx is going to be xi into fxi into dx. Sum of all this contribution is the integral. This quantity over all values of xi. So mean is going to be then therefore not dxi, it will be xi fxi dx, where x dx is varying from minus infinity to plus infinity. That is, this side it goes to minus infinity and this side the limit is up to plus infinity. So if it goes up, if we take the entire curve and if we want to, we have to find out the mean. So it will be xi into fxi dx, or xi varying from minus infinity to plus infinity. So all the values of x is considered here from the left hand side end to the right hand side end. And the variance is going to be, as shown it here. Similarly, it is going to be the deviation square multiplied by the probability density fxi into dx, and then we integrate it from minus infinity to plus infinity. That gives you the variance. So there is similarity in the equations between what we have seen earlier for the discrete distribution case and what we see now for the continuous distribution case. So exactly same approach.